models, and in the last few lectures, ZNN models.
Time varying case.
Time varying case. Okay. Now
Here we will present some models slightly above standard. Show again a ZNN model for solving linear matrix equations in time varying case. System of linear equations will be case. We will apply some system of linear equations. Computing eigenvalues where instead of eigenvalues and again x of t. So we consider a of t b of t x of t, here I will put. Error function is defined, of course, which means it is vector. First we consider it, of course, error function is a of t, x of t minus b of t. General rule is when this equation is equal to 0, then we will obtain, of course, solution of 35. Only one unit is a scalar vector matrix case, and even in matrix case of t, I will divide this step for better understanding. Is a dot x minus b of t. And it is equal to gamma e of t in expanded form. It can look relatively complicated in complicated form, but general rule is simple. And if we consider square case matrix, we spoke yesterday, it will not be completely correct, it will not be correct. Equal to, I will try immediately, x dot of t. We use sometimes v dot, sometimes x dot, a of t, x dot of t. You can see better from this distance, x of t. Minus gamma. And if we consider, if we want to work with, then solution is to consider normal equation form A transpose equal A transpose of t, B of t. Very efficient approach. Because B is not consistent, then normal equation form is this normal equation form corresponds to least square solutions. In case if T will be minus 1, A transpose B of T, A of T minus 1 A of T A dagger of T B of T. ZNN model in this normal equation case requires invertibility other.
Not visible.
Not visible. Because it is down. Solution is x of t equals A transpose T transpose A of T minus 1 A transpose of T B of T, which is equal to A dagger of T Moore-Penrose of T times B of T. ZNN in this case is normal equation case will be applicable if A transpose A is invertible. If not, finally, if even A transpose A is not invertible, then very famous approach, there is very famous approach to solve this problem, which enables application even in case when A transpose A is singular. It is so-called Tikhonov regularization. And we will consider A transpose of T, A of T, plus lambda identity matrix, X of T equals to A transpose T, B of T. When time tends to infinity, we will obtain solution plus lambda I minus 1 A transpose A plus lambda I will be invertible in arbitrary small. We will obtain approximate result. Again, during time, if time tends to infinity, A transpose of T is convergent to A dagger of T. And again, we will obtain approximation of Moore-Penrose inverse solution. It is approximation because so we have a system of linear equations. Ax equal b. First consider, then consider normal equation form is invertible. It is second step. If parameter plus lambda I. In this way, we will obtain regularity or invertibility of this matrix. I think that opposite to invertible is singular, but in literature, later research, it is relatively strange for me. Also, say regular matrix is okay, invertible. In role of this K means gamma, regularization parameter gamma. I spoke that in writing papers we must change notation sometimes, and here I put material from different papers, and because of that sometimes notation is different. Is simple. Input is matrix A, invertible matrix in this case. We need A, input is also vector B. We need to multiply matrix A with x of t. X of t is output from integrator. In integrator, we must define initial value. I will make double. We need Simulink. I found many Simulinks, A should be defined. Here is integrator, 1 by S, well-known notation for integration, integrator. Initial condition is initial time moment, t equals 0. We need the value x of 0. We will need value x of 0 because we didn't make computations in the right part of this Simulink model. It is initial state when we just started computation, and we will need initial value from here. It will be x of 0. Then we will multiply a by x of 0, a of t by x of a of 0, x of 0. Later, we will have another values of x of t in subsequent time instances. A. Here will be, in this short connection, will be which result will be here? This. What we multiply? A with x of t. A x of t. In positive part of this plus minus, which means a x of t will be used with sign plus, will be positive. B will be negative, and output of this block will be ax minus b. Then we can trace this Frobenius norm of this expression. Need because ax minus b is our residual error. We want to obtain ax of t minus b equal to 0. And vector during time. Here we used two workspace block for future analysis. and use the display block which will show current value of norm. Then nonlinear activation, denoted by G here, of course, can be denoted by several activation functions. Choose, here are switch activation function we will use. Other parameters. We spoke that typical finite time convergence is of the form absolute value plus absolute value of u 1 by q. Q is something between 0 and 1. Value is big. And we always have a trade-off between two terms. When Q is 1, another activation functions use some additional absolute value of U. In any case, don't forget that nonlinear activation function is based on odd and monotonically increasing function. Sine hyperbolic power 3 function, u power 3, it is one odd and monotonically increasing function. What is graph of this function? Can be used as nonlinear activation. It is another possibility here is here are two additional terms. Does not work. In any case, we can add more terms. Researchers want to put some additional terms and in this way regulate finite time convergence. Goal is to define finite in advance, put appropriate value and obtain convergence in predefined time. Output is nonlinear. We will use gamma. And here is minus gamma. Output is gamma, but here is sign minus, which will give minus gamma, and we need identity minus A times X dot. X dot is obtained here. This connection is X dot. It is A minus I X dot minus gamma F, calligraphic F, AX minus B. And this expression represents X dot. And we use this connection, made new connection, multiplied A minus I minus A by X dot. I will repeat again. This model is useful in solving matrix equations and even in solving a system of matrix equations. When we apply connected product and vectorization, we will obtain in result system of linear equations. Finally, we expect that model for solving linear matrix, linear equations, 35 will be able to find eigenvalues of matrix. Here is description of ZNN model for solving general linear matrix equation. Is this upper part visible? This part? Not. This part? Visible. I will write until here, approximately. We want to solve general linear matrix equation, which is of the form A of t, x of t, from GNN case. But model used here to solve this problem is different based on ZNN dynamics. Also here we assume that input matrices A, B, and C are time varying. X of t is our result. And clearly, error function will be defined as x of t, b of t. Excellent. Minus E dot of t. Probably will look complicated, but there is nothing complicated. We have three terms in product, and derivative will produce three terms. Then derivative of second term. Plus derivative of third term. No space for last term, minus C dot of t. And according to general ZNN model, E of t is equal to minus gamma, possible nonlinear activation, and error function. I can continue. It is equal to minus gamma A of t, B, X of t, B of t. As always, we are interested in term containing x dot and will obtain A of t. I will make one step more to be more clear. X dot B of t equals to minus A dot of t, X of t, B of t minus A of t, X of t, B dot of t, then plus, I think, plus C dot of t should go to another side. We will add from left X dot of t and from right X dot of t. This term will go right, and we will obtain here ei minus A of t. Cannot be in common because we have B of t also. Independently, X dot of t minus A of t, X dot of t, B of t, and then all another minus A dot one row more t plus C dot of t minus gamma E of t. Possible. Here can be nonlinear activation function. Looks complicated, but nothing is complicated here. Of course, corresponding Simulink also looks relatively complicated with many terms. It was necessary to compute such expression to obtain X dot integrator, then, and output is X dot is X. Sorry, X dot is input of integrator, X is output of integrator. First model is linear. Another model is nonlinear. There is included an activation function and a subsystem with different activation functions. It is difference between two models. It is one approach, direct approach, how to solve system or how to solve general linear matrix equation. There is another approach, possible simpler. This approach is based on application of vectorization and Kronecker product. Are you familiar with vectorization and Kronecker product? No, someone or yes? A is matrix, is complex matrix of order m times n. B is complex matrix of order p times q. Kronecker between A and B is of order MP times NQ, and it is defined as matrix A11B. It is practically block matrix because B here is matrix, and we can expand this block. It will be one P times Q matrix, A1, 2, B, and so on. Last element in first row. And it is correct. So on in last row we will have A M1 B, A M2B, so on till A M N B. And again, each product of element by matrix is matrix. If this element is new P times Q matrix, in general we have mn blocks of dimension P times Q, and overall dimensions is as we spoke. What will be vectorization? We assume that Ij defined as matrix A11, A1n, first row, last row, AM1 to AMN. Weights of A will be one big column vector. This vector obtains stacking column by column in one big column vector. So on till last column by column. And last column will be A1n to AMN. It is first column. We can denote this column by A1. Sometimes a notation for row is index. Index is column. Then second column. And last end column. Result is dimensions of this vector. This vector will belong to Mn times 1 is assumed. It will be, we have 10 minutes more, I think. Have more time. Here are stated main properties of vectorization. vectorization of A plus B is equal to vectorization of A plus vectorization of B. Vectorization of A, B, C is equal to C transpose Kronecker product of A vectorization of B. And according to this property, here is method how to compute vectorization of AB. We can consider we need to observe dimensions first. A is matrix of M times L order, B of C is of order, P times Q B is of order n times P. And here we can consider IP. And the result will be AB. Instead of C, we will have IP. And it will be IP Kronecker I vector B transpose last, Kronecker first, then vectorization of second of term in middle. But we can consider this expression in different way. For example, I will remove now this. Here we can consider matrix. It is true, I am. And we will obtain B transpose Kronecker I am width of A. It can be considered in two different ways, and it is frequently used. Any matrix problem we can transform in vector form. It will belong vector on right hand side. Matrix will be of big dimension, but a general model is system of linear equations. Even system of matrix equations can be considered in this form. We will consider one block error matrix. Error 1, error 2, error M, for example, and then we will see some of these models tomorrow, last day. It is our T, X of T, B of T equals C of T. That's of left, that's vectorization of left hand side, vectorization of right hand side. Vectorization of Kronecker first, that's of X. In general, to vectorization always, if here is only AX, we will consider I from this side. Always from this side. This unknown matrix must be middle, so that unknown matrix goes in long column vector. obtained after vectorization of this matrix equals that of C of t. And it is linear system of linear equations with, we must say, big coefficient matrix of relatively big dimensions, and if we replace this Kronecker product as P of t, evidently we will have linear system P of t vector. Notation small x of t here, and for example. And now it is visible linear system. ZNN model for solving linear system. I think now it P x equals B. I did in 43. Very gamma is not considered in constant. Chinese colleagues, then he suggested to use, there is not necessary to use approach is called varying parameter. So, of ZNN dynamics. So far, all those researchers put here gamma, and after that investigation, we used, can we use another approach to define gamma t? Exponential function. Here is gamma of t defined as exponential function of bt, and still here is gain parameter gamma. And we applied this model on investigated already, AFG of t G of t, A of t, two functions. G is of opposite dimensions of G. F matrix, we mentioned many different limiting expressions which will be obtained using this general exponential convergence rate. We spoke that has analytical solution in form E of t is equal to E of 0 exponent. Clearly here we can observe exponential convergence. E power minus gamma t tends to 0, evidently. As t tends to infinity. We will say that of ZNN is equal to gamma. Why? Because of this term, e power minus gamma t. Gamma is this exponential factor which defines exponential convergence rate. If we consider varying parameter ZNN model, we will have modified ZNN dynamics, still in form of ZNN dynamic E of t. Gamma is changeable during time. Then analytical solution will be E of 0 x of minus gamma of t. It means that exponential convergence rate of Vp ZNN is equal to gamma of t. And here in this theorem, we compared exponential convergence rates of Vp ZNN and ZNN, and always is possible to is greater than gamma, in which increases during gamma. Okay. We have small time to see what will be with vectorization of another matrix equation, a very popular and frequently used Sylvester equation. Here we presented vectorization and of general linear matrix equation Ax b equals c, and Shaban will present you shortly vectorization of Sylvester equation. Okay, Shaban, if you are ready, please. Which part of table do you want? Left? This one. It is better because it includes properties of vectorization. Includes properties of vectorization. Yes. Equals 0, or if we move C on, okay, it is the same. It will be minus C of t on A, B, C are given matrices.
Should I consider the regular ZNN first, or then first do the vectorization?
One approach is direct approach of ZNN, use derivatives. We want to consider here vectorization. What vectorization will say? What vectorization will say?
We want to consider this, the x of t, we want to vectorize it. So we will.
That's of x, vectorization of x must be always. So I from left or from right depends on position of x. X must be vectorized. Here we must consider I right from right. New from this lecture, new is first matrix equations is important. Then we learned about Kronecker product and vectorization. And according to this, we developed models for solving general linear matrix equation and Sylvester equation. And finally, we learned something about varying parameter ZNN. We started to modify ZNN, not only to apply. It's time to modify gamma, use varying parameter gamma of t. And better is to use gamma of t. in both cases, we need vectorization of x, and it can be connected in one term.
And then we can use regular.
And then system of linear matrix equations. And all is reduced on system of linear matrix equations, column vector B. You can think about this possibility if we have more errors.
Thank you very much. Okay. So if you have a
develop
If system is rectangular in time varying case, ZNN will
when the system is rectangular and it's like a very undetermined or least determined, we pad with zeros and make it square.
yes, you remember this can be applied to rectangular case, square matrix case, some zero columns or some zero rows, normal system. Square, definitely. But ZNN, we will add another term and use Tikhonov approach to rectangular case. Okay. 10 minutes for coffee break. Previously. Here is VP ZNN model. Can we start? Here is VP ZNN model. Z of t can be appropriately. When we started investigation, such approach or z power t plus z, always good choice is exponential term to increase convergence rate during time t. Here are different defined error function. Because of that, I decided here to put again, letters say that it is in matrix case. Here is A star A, we will obtain left inverse dual case, which leads to right inverse invertible or singular. We will use regularization. Here is error function for, so here is error function for computing square root of A of t. Result of this will be square root of A of t. Of course, if we force E of t to 0 using ZNN dynamic or another, we will obtain A of t. A of t should be positive definite. Model for computing matrix square root. Again, we can consider it is new matrix function which we want to compute using. We want to find square root of A of equation which we want to solve. Error function is defined as x of t is equal to, what will we do with x square? It will not be x square, will be x dot of t, x of t plus a dot of t. order, arbitrary order root. ZNN model gives, I will continue. And according to ZNN design, it is equal to now we need terms with x dot dot minus x of t, you are right, x of t, x dot of t. Can you see this? Gamma. Oh, plus a dot, yes. Plus a dot of t minus a of t. It is ZNN model. Again, in sim integrator here, input to all this. X is output of integrator. Inside the integrator, we must put initial state. It is spent enough time to put expressions corresponding to connections. First and second term, or first and third term, and because of that, here we have 4 plus minus signs. Here is one example with time varying matrix, exact solution as exact square root, experiments which compares, numerical experiment which compares linear and power sigmoid activation model. Blue graph is aimed to a nonlinear model with power sigmoid. In all 3 graphs, we consider also 1 second is obtained using, we can expect faster convergence, relatively stable, around 5, gamma 10, 0.5. And here is 0.0 with gamma. How to say? V of t. In the faster convergence to stable, relatively long rate here, approximate solution of time necessary. Main activation convergence is not if we remove here is versatile activation function with 2 additional tunable activation for 2 powers, but with cyan. Other kinds of 1 power value with 1 power and absolute value with opposite power. But here, 1 power and with these powers. Why it was useful? Convergence. Theoretical result, they are in dual king to predefined finite time. Of course, then computation is, it will make ZNN model. After 4 revisions, quickly neural processing. Interesting here. This model is defined, I can see 2 op Q by P, not so much. Q by P is less than 1. We will obtain finite time convergence. Can show K1 and K of the integers such that say this early powering. Otherwise, problem will be difficult. Each element of matrix is in elements of each. Approach was includes error function and varying parameter, time varying parameter, and general VPZ, and obtained many different cases. Standard ZNN. How we 70? K1 should be constant gamma. If we, without second term, 1, 0. If we use both K1 and K2 and fixed mu of t, proposed first time, and another choice, it was considered in one of previous publications. Expression in form gamma case of mu of t. C is value great here, and analyze finite time convergence. Find in form. The part is the same. Time in standard way, and of course all here is mu of t, and difference here is q by p. Why it is the case? E of t equals a of t, x of t, b of t, equal dot of t is in all cases independently of ZNN model, which is x of t, b of t, plus a of t, x, a of t, x of t, b dot of t, minus c dot of t. And if we want to apply ZNN, T of t. Of course, nonlinear activation is desirable here. If we want to apply varying parameter ZNN, we will say E dot of t is minus gamma of t, E of t. Particularly, we can choose here gamma c. How to write this? Power t, where c is greater than or equal to model. I cannot see name of this new model. VP, varying parameter, finite time, ZNN. We will have design E dot of t equals k1 e of t plus k2 e power q by p or p by q, q by p. In any case, must be less than 1 of t. The only difference is in this form minus gamma e of t or minus gamma of t e of t or minus gamma, and then this expression. Again, I will say q by p should be less than 1. When e of t tends to 0, this power will increase values of error function. Of these models, I will choose first one, ZNN we already investigated. Is a dot x of t b of t plus a dot a of t x dot of t b of t b dot of t minus c of t. It is e dot in all cases equal. In all, better not to write the same this way, and then equal is different. Here, most general case assumes here varying gain parameter gamma denoted by mu of t. I think it was okay. Because mu of t here is defined as gamma times power of xi by t, where xi is greater than or equal to e. X u of t k1 e of t. And again, we can do in the same way, add x plus left and right. It will not be visible, but if I go in right part of table, in any case, I will save properties of vectorization equals x dot of t times it minus a of t, a dot of t, x plus, it is different. It will be fixed, different parity, non-linear activation t, but consider k1 e of t plus similar approach is to use k1 power where p is greater than 0. E of t. Of course, we can write. We will obtain nothing. I think we change problem which we want to solve. E of t will be different here. Of t q by p is our VP fit ft ZNN. VP ft ZNN model. Requires a lot of details. Theoretical result. Something I will show you is defined as matrix with an FT-ZNN model with this mu of t defined as gamma K1 and K2 parameters. It says it is finite time convergence. No infinite time convergence will be finite time. But again, increase gamma even to infinity, we will know logarithm of xi to be e, and then this way will be and in general 1 by and then logarithm. A plus is e plus different activation functions which are ZNN standard finite time ZNN. ZNN, do you remember, is defined using E is equal to minus gamma E of t. Finite time Z minus gamma. What was here? Can say 1 power. It was in opposite of t always. ZNN 1x is minus gamma E of t plus k2 e power greater than or equal to e. And here is comparison finite time convergent ZNN models, and one ZNN model goes to infinite time convergence. Next is, I will change again varying gamma. It looks as not finite time convergent. Term which enables faster convergence. It is red line, but still quickly, but goes to 0 after infinite time. And two considered. Green is well known, previously published finite time gamma, and two terms, scalar parameter power p of error function plus new scalar parameter power 1 by p of error function. And best black graph is for proposed VP FTZNN design in this paper. Dot of error function is defined as minus gamma and then power of where xi is greater than or equal to e, and here is second one is parameter k2 error function on power e of t goes to 0, this term will increase. Here we made the unification of finite time convergence and about varying parameter mu of t. First graph is made using gamma equal 1. No need to use big gamma. Second graph is made using gamma equal to 2. What is interesting to mention here? Xi power t. Xi is greater than E. Simulink model. Time starts from 0 and goes to end. This end must be greater than 0. And in this way, what will be with Xi power t will increase. And during time, during evaluation of our VP FT ZNN model, this term will increase and convergence will be faster and faster. Gamma equal 1 is enough, right? Gamma equal 2 is enough. For VP ZNN, but VP ZNN includes one exponential term, much faster convergence, but not finite time convergence. Here is visible black graph quickly, immediately after 0.5 goes to 0. In case gamma equal 2, we found faster convergence. VP FT ZNN obtains 0 before 0.5. ZNN is slightly faster, but still far from convergence. Red, ZNN with infinite convergence. Here is infinite convergence. Numerically is okay, obtain accuracy 10 power minus 6 minus 9, but theoretically 0 is achieved in green case and in black case. Green case is first finite time convergence ZNN model. Black was improvement of this finite time ZNN model. Is it possible to define future improvements of finite time convergent models? Possible?
Just like in VAF activation function, we can use.
After that, people used E of t only. Here we can put inside E of t. Tunable activation function enables something between. Then after that, it is possible to consider some terms, another parameter time t plus, if you want to regulate complexity during commutation. Always it is possible to include new terms to obtain finite convergence. Many people will say, oh, I will use here bigger Xi. Of course, possible to use bigger Xi. We wanted something better than E used in VG RZNN model. Some other terms can give some result, but not so interesting results. Here is estimation of finite time convergence. Lie activation function gives finite time convergence expressed by 74. E plus is maximum value in error function E of 0. E of 0 is initial state matrix, and according to initial state matrix, final initial state matrix, another matrix here is what we used, sign, and then plus plus 2 again. Here is final time convergence. Finally, we can see in 76, A3 and A4 have no influence on this estimation. A1 and A2 are important, and powers P and W are important. 1 by P means that P should be less than 1. W minus 1 means W should be greater than 1. Of course, always one exponent less than 1, another exponent greater than 1. Here, in our definition of VP, FT, ZNN, we used here 1. Different combinations are possible. Here is this complicated case. Terms with power greater than 1 given in such summation. Power less than 1 another is given as another summation. And so on, so on. It is one modification of gradient neural network. Tomorrow we will present this modification of gradient neural network. We will present high order neural network. I hope we will have enough time to present combination of GNN and ZNN with I plus AA transpose factors, integration enhanced with integral term. And I want to show you about mathematical multiply from left and right to obtain result in 2 hours, in 2 lectures. But we can, we could say more, but it will be faster, I'm afraid. I was between to be not so fast and say more slow, and another goal function is to say more. Okay, we can start with questions. Shabam wants to.
Hello. Instead of directly solving the matrix differential equations, where we treat each element as a separate differential equation, will it be more faster or model, more accurate?
E dot equal, for example, simplest case, minus gamma E of t is in the matrix form, and it assumes one system of ordinary differential equations. Solving this system is this problem using GPU, and could not find so far. What is problem if we use GPU and MATLAB solver? But I think it will be possible to solve. If we use GPU or arbitrary parallel processing, then we will solve questions, but each ODE is independent of all another, and fine job for parallelization. But you think about.
And also for the weights that we use, like K1,
K1.
K2, P,
Uh-huh.
Q. So
Uh-huh.
can we use any another architecture to find its optimal value instead of just putting it randomly?
Instead of K1 and K2,
We take random values, hit and trial method to find the values.
K1 and K2, real
So
numbers.
instead of can we put any another architecture to find the optimal? Can we convert it to optimization problem to find the weights?
Find optimal values of K1 and K2. Looks difficultly. Which kind of optimization problem we have. One possibility is, I didn't think about this so far, to consider K1 of T and K2 of T, for example. But if we want optimal values of K1 and K2, we must define optimization problem first. If we do something and propose appropriate optimization method, it is possible. You are young and you have time to think about this. More questions, Sharon?
The power when the Q upon P thing, it behavior drastically changes when we take either tends to 0 or tends to 1 or tends to 0.5.
Depends on P and Q.
So which it will change according to problem, or it will always give right amount of results with tends to 0.5.
According to problem. I don't know method. I don't know method which will say this class of problems K2. Try and see. There is always possibility to make trade-off between K1, K2, P and Q. And so far we have no theoretical results which will say is optimal. Probably it is possible to investigate Q by P less than 1. If it is better Q by P to choose near 1 or smaller values. We didn't investigate so far, but for example, it looks possible. According, it is included in definition of square root of matrix.
So how do we ensure that for different time of t, AT is positive definite matrix?
If it is not positive definite, behavior will not be
Behavior.
good. Behavior will not be good. It is also situation for investigation. In any case, square root requires positive definite matrix. What is inside if this requirement about positive definiteness is not satisfied, ZNN will not show good behavior.
So it depends on the parameter.
Depends on
Parameter T.
parameter T. And I'm not sure, but it is possible that during time will be possible A of T to become negative
I
definite.
think, okay, A transpose and A always positive definite. Whatever the value of positive definite, whatever the value of T is.
What will be with arbitrary A
Yes.
of T?
So it is parameter independent, you can say.
ZNN is how to say, always applicable to time varying case. We can apply to constant case, but there is no, how to say.
Any other questions? If no, please give big thanks to Professor Fredrak. Have some quiz exam. Okay. So today I'll discuss LE decomposition and other factorizations as well. Okay, this part we have discussed a lot of things on the backward error, stability point arithmetic in numerical computing, and this emphasizing tool. So basically, we'll need to things on the backward error, stability point arithmetic in numerical. So basically, we'll so here willing point number, the based on the scientific notation, and for example, this is the number is a normalized form, quantify is non-zero. This is first digit is non-zero. So if you have this number, say for example, these two non-zero numbers after decimal, then you have to make it to normalized. Okay. So when would be overflow and this underflow, the number 10 to the power 55 into 10 to the power 50. Okay. It depends on whether you are okay, and the results are too small is represented, and the underflows are often set to zero, state 0 instead of some numbers. You make a proper scaling. And basically we use this I. Okay, so it means it takes the longer length of the number. So that's why we prefer this. And say for example, in single precision we to the power 38. Okay, and if you have double precision, 10 to the power 038 to 10 to the power 308 digits. As I told you many times that in determinant, for finding determinant, you are subtracting two numbers and you are losing a lot of things. You say x minus y and 0.1, and you are loss of significant digit. Okay, clear? And what is the forward error? Forward error analysis. Other one is called backward error analysis. Okay, and more often you do by problem that the computed solutions exactly solve. Okay, and they track the propagation of implies the small errors behave as if from slightly perturbing small in the output, that you can say that this is backward stability. Okay, are inevitable in floating point arithmetic, and IEEE standard provide representing the computer basically represent. The backward error analysis is a powerful tool to assess the cumulative effects of round of errors in computation and introduce the notation for the floating point results like floating point. Okay, so every time you are putting the floating point of C instead of C. Okay, so how it comes, just you see. So when you put this, then floating point of C is nothing but C plus epsilon. This is called absolute error. This epsilon is called absolute error divided by the exact number, this C. And this, if you write this, if you just input this epsilon equal to C into epsilon relative, then you will see epsilon relative equal to this is the relative error, and this is the number, exact number, and this is the error term like C into 1 plus epsilon relative. Okay, so we basically we take this floating point relative error. And you see this is the scale independent. If you do scale, take this. Say for example, here you see the computation on a 7-digit decimal machine. So if this is absolute error, this is an absolute error. So, epsilon relative is this. This is 2.91 into 10 to the power minus this 2.288 into 10 to the power. So, that is why we use this is scale independent. Okay. So, that is why it is preferable. Use this relative error. Now, relative error accounts for the scale of the exact result. Relative error is more useful when comparing accuracy with the relative errors. Okay. These are some information. Now, you see absolute error has the same units as the quantity, volts, seconds are the difference. It has units and it has no units. Technique, we use relative error instead of absolute error. This is the reason. This is the error and this is the exact value. This is the relative error, and if you change the entries of the matrix, this is your requirement. All measure relative error, okay, the percentage of error. Correct digits information. The operations are exact, result is then rounded to the nearest. Your overflow and underflow kind of things won't happen in your. Now, here what is the unit round of error? So, for the single bit how much it is. For the double maximum relative error in a single rounding depends on the number of digits in mantissa. For the single precision, this u is nothing but 2 to the power minus 24, and this is exactly approximately equal to 6 or 8 digit decimal places. And for the double precision, unit round of error is 2 used to tell this is accurate to 16 decimal places. And if it is single, the single precision, and this is unit round of error for the double precision. So, when you do the what would be the unit round of error? If that much error you are accumulating, that means your things are stable, your calculation is numerically stable. Okay. We use this relative error, and this error is should be less than equal to unit round of error. That means it is numerically stable. If I will put this C, and if it will each operation introduces a small error, each operation is a small error. Does this mean many operations are always safe? No. Then error will be exponentially, it will increase. Okay. If you are not doing with this, especially if data is already perturbed. So, sometimes you have to check if each step is accurate, and accumulated results can still be already perturbed if you have perturbing your data. So, what exactly we are doing? If you put in your machine x, if you are giving, and that number will be taken instead of x, your MATLAB will take, or Mathematica would be taking like this. Okay. And this y equal to y into 1 plus epsilon 2, and the epsilon and compute this floating point x y. This is x epsilon 1, you just do x into 1 plus epsilon 1, y replaced by y into 1 plus epsilon, and total floating point if you open, that would be 1 plus epsilon 3. Yes, y 1 plus epsilon 1 plus epsilon 2 plus epsilon 3. Understood my point? So, if you just divide this, I have made some calculation, the floating point of x y into 1 plus epsilon, and these numbers you can put this epsilon 1 plus epsilon 2 epsilon 3 as a epsilon. This would be floating point of x y equal to x y into 1 plus epsilon, and if these numbers are less than unit round of error, this sum would be less than unit round of error. Okay. This floating point of x y, you are taking this x y, this x into say x into that means the floating point of, first you write x into 1 plus epsilon 1, this, and y into 1 plus epsilon 2, and whole into 1 plus epsilon 3. Okay. So, first it calculate the floating point of x, then floating point of y, then whole into floating point of this one. Okay. So, floating point of x, it calculates this 1 plus epsilon 1 and this 1 plus and whole into 1 plus epsilon 3. If you do product and you remove these higher terms, you will get this higher terms, you will be getting 1 plus epsilon 2, 1 plus epsilon 3, is not it? Epsilon 3 and plus epsilon 1, epsilon 2 plus epsilon 2, epsilon 3 and epsilon 1 these numbers you will be getting. So, these numbers, because these are the unit rounds, epsilon I, this is less than unit round higher terms. Okay, you are ignoring this because x y, this you are keeping this ultimately equal to this one. So, you are ignoring the higher terms. Okay, and epsilon, and where epsilon equal to epsilon 1 plus epsilon 2, 1 plus epsilon 2 plus epsilon 3, and again it is less than round of error. They should be again less than round of error. Okay. So, if you put the number x, it will calculate this one. There are many other errors are included. Epsilon, okay, as I told you, this is epsilon. This is approximately equal to this one. Behaved under the floating point rounding error. So, if you adopt this technique, that means okay. Relative errors preferred due to the scale invariance and interpretability, because this is scale independent, as I told you. Unit round carefully analysis is essential. Multiplication and division behave division also. So, if you have number, you just do divide this one x y x, you can finally you will get this 1 plus is nothing but this one. Okay, because this 1 plus epsilon 1 into 1 plus epsilon 2 you just okay. Clear? So, division is well behaved computing your results. Okay. Similarly, as you have seen the floating, this is x plus y into 1 plus epsilon 1, and you make this floating point of x, floating point of y, and whole into floating point of x to 1 plus epsilon. Same way you have to do the floating point of x plus y. So, you will be calculating this floating point of y, this one, and this is floating point of, this is x into say 1 plus epsilon 1, and this is y into 1 plus epsilon 2, okay, and you remove this x into 1 plus epsilon 1 plus y into epsilon 2, and this way you are doing, and just you multiply this, and you have this x into 1 plus epsilon 1 into 1 plus epsilon 3, okay, and this x you have this 1 plus epsilon 3 plus epsilon 1 plus epsilon 1 epsilon 2 plus epsilon 2 epsilon 3, okay. Yes or no? X plus y, and you just add this number x plus y 1 plus epsilon 3 plus epsilon 1, and you are just ignoring the, okay. Clear? Then here you are taking this x plus y, it will come, and then you can say x into epsilon 3 plus epsilon 1, and this is y. So, just take this x plus y into common, this 1 plus x divided by x plus y, epsilon 3 plus epsilon 1, and plus this, is not it, and this approximately equal to x plus y whole into 1 plus this epsilon 3 epsilon 1, and this is plus this 1 plus epsilon 3 1 plus epsilon 3 plus epsilon 2, okay. Yes. Oh, here there is no one. Here. This one. There is no one. We come here. Okay. That's why. Now here this x plus y. This 1 plus, you take this as a epsilon, 1 plus epsilon 1 2 epsilon 3 plus epsilon 1 and this is plus epsilon 2, and this is less than or equal to, this is very small numbers, this is less than or equal to unit round of error, UV error. Okay. So, all the calculation, this floating point of x plus y, x less than unit round of error. Okay. All this calculation, because if you do product to unit round of, again it would be less than unit round of error, because again it is a smaller number. So, accuracy if x and y are not close to cancelling each other. So, here is this, if x is approximately equal to minus y, then x plus y equal to 0. So, this is the case where you would get the problem, okay? Because x is, if it is approximately equal to minus y, then x plus y, because you are dividing this x plus y, that is why it is telling x plus y you are dividing. If this is close to minus y, then it would be 0 and you have the large relative error. So, you have to be careful whether x is approximately equal to minus y. Okay. Otherwise, things, when does it happen? When two large nearly equal quantities are subtracted and most digits cancel, leaving a small difference with poor relative error. If this cancellation will happen when the large nearly equal quantities are subtracted, because very near number if you will subtract. Okay. If the matrix entries are very dense, that means they are approximately equal, means in that case this large relative error would come in. So, as I told you in my last class, that if eigenvalues are very close to each other and if you are making difference, that means they are near to each other. So, in that case it would be large, this one and y equal to the, and you just to subtract 1.5 into 10 to the power minus 6, this is very near to 7. And input errors 10 to the power minus 7, 7 accurate digits, and output error is 36. So, this is the difference you have in the single bit calculation. Gradual accumulation of small errors, slow, often tolerable, and there is a, these are the error, catastrophic cancellation, and if you do cancellation also you will get this error, sudden dangerous loss of digits you will happen. So, that kind of cancellation if you do, then you can get the dangerous loss of digits. If a computation becomes inaccurate, there was likely cancellation. If no cancellation occurs and inputs are accurate, output, in that case cancellation will not happen and you will get the generally accurate results. So, hard to prove when, where the cancellation will happen. So, try to bound the error at each step of an algorithm, must show either no cancellation happens or cancellation won't degrade. Usually impossible to guarantee in general, motivates development of alternative approach like backward error and the other things. So, for that you have to think about the backward error analysis. Okay. So, all these things, cancellation, how you will take. Okay, you ask this, is this computed result the exact answer to a slightly perturbed input? As I told you, if we are coming from far from the exact solution and you think about, if you think that error analysis, say for example, if you are giving say two numbers in, then it is g. So, floating point of x plus y plus g, and this is floating point plus epsilon 1, and for g you get another 1 plus epsilon 2, this is for x plus y into 1 plus epsilon 1, things you would be getting here. So, d plus y tilde and z tilde is not it, you just maintain this and perturb x and slightly perturb y and slightly perturb z. Now, this result C is the exact sum of x tilde and y tilde z tilde. Function, say for example, if you have the function with the m variables, say g1, g2, gm with small perturbation and gm with g1 tilde up to gm tilde. So, if it is the m change gi plus delta gi minus gi, this is very less than the gi, small nearby problem. As I told you, if it produce the exact solution to a nearby is there, you got x tilde and you change the small in the input matrix delta A, and that delta A. Conclude that computed result is accurate, we need the backward stable algorithm. The algorithm gives exact solution to a nearby small change in the output. If you change small and you change the, and you are getting a small change in the output. And if you do small change in input and if you are getting large change in the, if both hold, then the computed result is accurate. Either it is backward stable algorithm and this one condition problem. If both in the Gaussian elimination, and you have seen the partial pivoting with the floating point error, with the complete pivoting. So generally you have this, and the problem's sensitivity and the backward stability plus well condition, as I told you before, the accurate result. Ill condition, if the problem is ill condition, even stable algorithm would give you the wrong result sometimes. Okay, ill conditioning problem only. It is an algorithm is satisfactory if it is backward stable. Okay, algorithm is satisfactory if it is backward stable. Now, this forward error and the backward error, this is here error in the input. This is the difference. Here you are calculating the error in the output, but here you are calculating error in input. Hard to account for the cancellation, always it is feasible and separates the algorithm and the problems, and rarely successful in general. Forward error analysis is rarely successful, as I told you before, that if the problem is backward stable, backward analysis stable, and then it is forward stable. So, not from this to this and this to this. Backward means this is forward, and forward it does not imply the backward. So, here you see, if you have this A x equal to b and you have the residual r equal to b minus A x, and say if you do compute, you will not get the exact A x equal to b, you will be getting A x approximately equal to b. If it is approximately equal to b, then means you will get the residual r equal to b minus x. And now you define this delta A, this r x t divided by norm of x square, and this delta A, you can see this would be the exact solution of this A plus delta A x equal to b. So, this is the approximate solution, and this approximate solution, this becomes the exact solution of the A plus delta A problem. And this residual norm is small relative to this, then the algorithm is backward stable. Okay, is relative to this error. If this is small, this is residual to relative to this one, then the algorithm is backward stable, and this is your backward error. So, this is the input, the error in the input, this is called backward error, and this is the error which is coming this. The backward error analysis central to modern numerical analysis. It shows that many algorithms are reliable even in the floating point arithmetic. Okay, small residual solution to a nearby problem. If the residuals are very small, then you are getting nearly the solution to the nearby problem, and backward stability and good conditioning, that accurate results. Okay, and always you check the residual. If it is small, then you can predict something. If your residual is small, your solution is trustworthy. That means it is accurate. Now, what the MATLAB, how you take the unit round of error. Say for example, MATLAB code you have this A equal to 1 and U equal to 1, this one, B equal to A plus U, and while B not equal to A and U equal to 0.5 into unit round of error and B equal to A plus U. That means this is your desired calculation with the unit round of error, and you have this U round of U. The observation is the loop stop when A plus U equal to A, this is the error and this is unit round of error, and if it is till the unit round of error, then you will get the A, otherwise the loop will calculate again and again, because If it is more than unit round of error, the loop will continue until you will get this error. Okay. So, the tolerance what you are putting for the single and the double. So, you can decide whether you are giving the single and double. Accordingly, you can get this. U is now too small to affect A in floating point arithmetic. So, U is very small and too small to affect A in floating point arithmetic. So, this is means A equal to A. 1 and this A not equal to infimum, then you have this A equal to, you have seen infinity, and this demonstrates a floating point overflow. As I told you, this is going overflow. So, if you replace with the 2, you can see the more often this. So, here is another MATLAB code. You can see that if A not equal to 0 and A equal to 0.1 and star U, this IEEE number, and you have also subnormalized number also, a very small, but does not vanish immediately. And this demonstrates. So, for finding this IEEE and this IEEE and help infimum, you will get this non means not a number. I want to discuss what is the floating point number. Say for example, the largest, and here also S digit and this one, and here a gap between this the S significant digit, here is also S significant digit. Largest rounding error occurs here. Now, try to implementing this test, the machine epsilon, that is machine error, and this overflow and underflow. Finite precision arithmetic can corrupt the Gaussian elimination, causes the nearly linearly dependent rows. Columns are nearly linearly dependent, and cancellation errors creating modify errors in multipliers and divisors in back substitution can be inaccurate. So, all this a non-singular matrix may appear singular. Why? Here is one example here, as you have seen part. Things more or less. Say for example, I varies from 1 to n. You have, if you are adding this, because already you have added 2 numbers, 3 numbers, and similarly you can add n numbers. Okay. So, for example, if you have 4 to this, okay, and sometimes you are adding this, but in generally floating point arithmetic we are doing this kind of calculation. This sum of Wi equal to 0, because typically minor, but may become the significant in the presence of cancellation. Okay. This if you have. Now, you see, if you 2 numbers you have as a alpha 2 and order of u square, where this alpha 1 and alpha 2 are around to unit round of error, then beta is the order of unit round of error. Put in the computer, instead of S, it will take escape. Escape in the sense that if escape is nothing but 1 plus the n minus 1 into u order of u square. So, if you add this n numbers vector, j varies from 1 to n, number of vectors from j equal to 1 to n, and induction. Say for example, it is true for n equal to 1, and also this is also true for n equal to 3. Assume that this is true for it works. Suppose the result holds for all n less than m. Okay. So, you are breaking into 2 parts, j varies from 1 to n, we are taking j varies from 1 to m. Okay. So, if and this is also k plus 1 to m, and this number is less than n, m equal to k, because k is less than m. Okay. So, writing this is k minus 1, j varies from 1 to k. Okay. And similarly, here you have this m minus k minus 1, because k minus 1, this k is k less than m, this one. To follow the induction hypothesis, m minus k is always less than m. Okay. So now what you have, this is escape, that means this is S1, we have broken into two parts. This is S1, apply the floating point arithmetic. This one is floating point of S1, floating, so 1 plus beta, you can get beta mod equal to this one. So this means this escape is 1 plus epsilon 1, because floating point of S1 cap, it is nothing but this into 1 of S2 is this much, and this 1 plus epsilon dash, and epsilon dash are about the unit round of error, and 1 plus, and this multiplication term, these are the unit round of error. This is the order of u square, this is also order of u square. So alpha plus alpha dash plus beta, error alpha dash, beta also unit round of, so its multiplication is unit round of error. Okay. Now this mod gamma 1, and this is nothing but k minus 1 plus m minus k minus 1, because this is helpful, this one, because this k minus 1 into u, m minus k minus 1 into, so all you are combining both at it, because this all you have combined this one. Okay. So finally you are getting this, that the accumulated floating point sum n terms, you will get this gamma n less than n minus 1 into u plus order of u square. So as you have taken the j varies from 1 to m, so here m minus 1 into u, gamma m mod less than gamma m minus 1 into u plus order of u square, because our sum was m and in the earlier steps. So we have applied the induction hypothesis to prove this number, that if you add n numbers, you will be getting this number instead of this only in the computer with the error this. Okay. So that means you know how much error you would be accumulating when calculating the sum of this n numbers. Okay, with the floating point arithmetic. Okay. If you are doing in this way, that means your calculation is numerically stable. This bound is independent of the order of addition, and this proves backward stability of summation in the floating point arithmetic. Like you told many times that in which way we multiply or add, so that we will get the things in numerically stable way. This is the way you just do this your calculation, and you will get the backward stability. Okay. Now this, the quantity gamma j are relative backward error, and this gamma j would be satisfying this one, is mathematically valid. It often over each omega j participates it at most n minus 1 addition, hence accumulates that many errors. In practice, most wj participate in far fewer operations, and this magnitude of round of error, each round of is at most u, but typically round offs are much unit round of error. Round of errors may partially cancel out instead of compounding. The bound assumes a worst case scenario where all the errors reinforce each other. And similarly, the way we have seen that Gaussian elimination without pivoting is sometimes it is unstable, and if you do calculate with the floating point arithmetic, that calculation would be arithmetic, floating point arithmetic. Okay. The backward stability, here you have, if G is a non-singular matrix, and how you compute this G y equal to B using the backward substitution and with the floating point arithmetics. So for example, if you have matrix C, say all these entities are the Cij, and we are taking this C mod, this is the component wise absolute value of the matrix. Okay. And C is less than F in the sense that each of the end matrix, okay, each term is given by. So now if you do backward stability analysis for the backward substitution, so like if G is a lower triangular matrix, and if G is a non-singular and a lower triangular, and B not equal to 0, if the system Gy equal to B is solved using the floating point arithmetic, as I told you, floating point arithmetic. Earlier whatever we have calculated without floating point algorithm, and we have seen that the calculation is without pivoting when the matrices are ill conditioned. So if the matrices are ill conditioned, so you just follow the floating point arithmetic calculations. So if you do floating point arithmetic calculation, the whatever the solution you will get, you won't get the exact solution. You would be getting the solution which is far from, which is beyond to your exact solution. Instead of y delta g, and this yk becomes the exact solution of g plus delta g. Okay, so yk equal to this one, and this delta g, this error and the backward error, this delta g less than equal to 2n u, u is the unit round of error, and g mod equal to this delta g ij. It means this is less than 2 nu g ij, each of the entry. Okay, plus the g means you have this is delta g ij, and g mod means this is each entry satisfying 2 nu into g mod g plus all of u square. And each computed component of y put delta g, whatever we have done with this error analysis, delta g mod less than equal to 2 nu times g mod plus all of u square. Okay, if this condition will satisfy, that means delta you are calculating. So this is important, that gy you are getting gyb instead of the small change problem, the g plus delta g, and this delta g would be satisfying with the terms of unit round of error. Okay, so that error, you know how much error would be either single or double, you can calculate. So similarly, if you have the this is the for lower triangular matrix, and if you have upper triangular matrix also same delta u and yk equal to b, and where delta u would be satisfying this term. So instead of lower triangular, you can have the upper triangular. Understood my point? So once you have the solved gy equal to b, and you have solved this you say we have seen this lu x equal to b, and this is g lg equal to b. Okay, here L means this is G matrix. So once you solve this equal to G. So the way you did this and you try to do this, similarly the calculation of LU. LU also, when you compute, you follow the same process, and then finally you get this Ax equal to B by using the LU decomposition with the stable way of decomposition of this L and U with the floating point arithmetics. So once you use this floating point arithmetics way, you will get all these things. Problem is ill condition, and you will get the solution, and always you will get the solution to the nearby problems. How much time it is?
Okay.
Should we stop here? We'll stop. Okay.
Almost 3 half past 3.
Okay. So if you have any questions, so we can discuss. So these are the highlights I have given, that how numerically it is coming beyond from your solution, is not it? We got a lot of examples. So if you follow the backward stable way, and you have to adapt the floating point arithmetics calculations each time. Okay, clear? Yes. You have any questions?
In real-time applications, like as you mentioned, ill condition, there is no guarantee whether an inaccurate result will come or not. Usually it is inaccurate. So when we are dealing with such matrices, besides backward stability, is there anything we can do to handle those ill conditioned matrices? Like some sort of synthetic data backward, ensuring backward stability?
Apart from this backward stability, I don't know how to control this, because this is the only way we can see in the perfect way whether our problem is getting right solution or you have the numerically stable solution, because all we follow the floating point arithmetics and unit round of error, all these things. This is a real thing, following like this way to get the solution. because this is especially when the matrices are ill conditioned, but if it is not ill conditioned, then it is thorough, you will get the solution. That problem is use this technique because this sometimes it is typical and it is hard to calculate, and some their own way, some technique they follow, maybe, I don't know. Yeah, any other question? Be in the perfect way, is not it? Because a lot of cancellation, addition, subtractions, all you have to count with the terms of unit round of error. So this is the standard results in numerical linear algebra book. You can find how you can compute the LU decomposition in a stable way, okay, if the matrices are ill conditions. Okay. So if no questions, we will stop here. Thank you.